In this video, we're going to talk about concavity. So let's define a function, f of x is equal to x to the third. And let's draw this out. So we have our y-axis, and we have our x-axis. And we should know that an x to the third function looks something like this. Oops, I gotta go through the origin. Yeah, that's pretty good. So concavity is essentially it has to do with the shape of the graph, and I want to first actually define it mathematically, and then we will define it more qualitatively. So the way we figure out concavity is using high order derivatives, and specifically the second derivative. So in this case, let's take the first derivative of the function, which is f prime of x, and if we do that, we get 3x squared. Now let's take the second derivative of the function, which is f double prime of x, and that's equal to 6x. So again, first I'm going to define it mathematically, and I think mathematically actually this makes a bit more sense, and then afterwards I'll define it, I'll try to define it qualitatively. So if f double prime of x is greater than 0, this is defined to be concave up, or you could say concavity up. So again, if double prime of x is greater than 0, this is concave up. And then now if double prime of x is, again, this is for any function, but we're going to use this specific example to define it more intuitively. But if double prime of x is less than 0, this is concave down. And f double prime of x is equal to 0, this is called an inflection point. Inflection point. And essentially what an inflection point means is the point at which the concavity of a function changes. Alright, so this is the mathematical definition of it, and I really like this mathematical definition. I think it explains it pretty well qualitatively as well, but let's talk about this a little bit more intuitively. So what does it mean for f double prime of x to be greater than 0? So in terms of derivatives, what it means is the rate of change of the rate of change is positive. So what that means is that the rate of change is actually increasing. So a way you could think of this is, let's say we have a car, we have some sort of car that is going with a speed v, or velocity v, this way, and it speeds up, right? So the velocity would be the derivative of the position function, and it speeds up to another velocity v2, which is greater than v. Now, for it to get from v to v2, it needs to have an acceleration, and that acceleration is the second derivative of position. Now, if that didn't make sense, that should make sense if you've taken physics. I think that's a great explanation for second derivatives, but if that didn't make sense, don't worry. I'm going to explain it in some other way right now. So, again, what it means for second derivative is the rate of change of the rate of change. So if we have, let's say, I'm going to draw a separate graph. Let's say we have a graph that's like this. So we know that this is a square root graph, right? And it's always increasing. But notice that the rate of increase is decreasing. So again, this graph is increasing, right? It's always increasing, and it's just going to keep increasing. But it's going to increase less and less as x goes to infinity, right? So what this means is the rate of increase is decreasing, right? So this means that the double derivative is less than 0. And so for that reason, it's concave down. So it's shaped like this. It's concave down. So this portion is concave down. Now, similarly, or actually conversely, for this graph, the portion where x is positive, we notice that this is increasing, and it looks like the rate of increase is increasing, right? So what that means is that the second derivative here, so from x is 0 to infinity, we have f double prime of x is greater than 0, right? The rate of increase is increasing. Now, this point right here is the inflection point because the concavity changes, or the second derivative goes from negative to positive. Let's actually talk about why r here is negative first. So this is concave up, right? So this is concave up on the right, concave up, which is again the same thing as that. And on the left, let's see. So again, the graph is increasing on the left as well to all the way to 0. It's increasing. But notice how the rate of increase is decreasing. Again, the rate of increase is decreasing here, right? So we can say here that the f double prime of x is less than 0. And this is concave down. And then for the domain which the f double prime of x is less than 0, in other words, concave down, is, well, negative infinity to 0. And the point of inflection is this right here. So x equals 0 is the point of inflection, where the double derivative is equal to 0. And what that means is that the rate of the rate of increase is 0. And that's the point at which the concavity of the graph changes. So we'll call that inflection point. Inflection point. So what we can do with concavity is we can actually, it helps us graph things. So if we have, for example, f of x is equal to x to the third and we don't know how to graph it, we can do a few things, such as find its concavity, find where it's 0, its inflection point, etc., to help us graph it. So again, this graph is concave down from negative infinity to 0 because the rate of increase is decreasing. At 0, it changes concavity from concave down to concave up because the rate of increase is now increasing. So f double prime of x is greater than 0, so it's concave up. So this is concave down. This point right here is no concavity, inflection point, and this portion of the graph is concave up. All right, talk to you guys in the next video.